Hello everyone. First of all, I would like to give thank you to the organizer for this event and give me opportunity to present our work. Let me introduce myself. I am Mohammad Tariqul Islam, master's student from University of Campinas, Brazil. Today's presentation title is HTTP Adaptive Streaming Based Empirical Quality of Experience Study over TCP and QUIC on Diverse Networks. This presentation is structured as follows. First, I will give a brief introduction. Then I will discuss about relevant background and objective of our work. Next, I will thoroughly talk about our experimental setup with two sets of experiment and their results. And lastly, conclusion with future directions. Now I will move on introduction. Online video streaming traffic has become the most dominant application on today's internet. A significant number of video on demand contents are provided through over-the-top platforms such as Netflix, HBO. Recent studies from Cisco and others predict in future video traffic will take a large portion of total internet traffic. The video streaming content providers adopt HTTP Adaptive Streaming standard to deliver the video on demand contents, wherein client-side adaptive bitrate streaming algorithms aims to select appropriate video quality based on network status to provide an interrupt-free video streaming service so that end-user perceived proper quality of experience. Initially, HTTP Adaptive Streaming built over TCP transport. In spite of reliability and in-order delivery benefits, TCP suffers from head-of-line blocking problem, which creates a barrier to ensure proper quality of experience. Therefore, QUIC, a new transport protocol, has emerged to overcome TCP's limitation and improve overall quality of experience. Background. Let's discuss about the logic behind HTTP Adaptive Streaming. HTTP Adaptive Streaming works by breaking the video content into a sequence of small segments. The duration of each segment could be between 2 and 10 seconds. Each of the segments encoded with different bit rates and resolutions. Among different implementations of HTTP Adaptive Streaming, the most widely used format is Dash or Dynamic Adaptive Streaming over HTTP. In Dash, at server side, each of the segment structure described in an empty file. On the other hand, at client-side video player, the adaptive bitrate streaming algorithms or ABS algorithms are responsible for dynamically select appropriate segment based on current network condition. Client-side player first download the MPD file and then it start to request the individual segment according to MPD information. The objective of dynamic segment selection to adapt the changes in the network condition and provide smooth streaming service. ABS algorithms are made on three strategies: RAID-based, buffer-based, and hybrid. In RAID-based, it estimates bandwidth before segment selection. In buffer-based, it monitors status of playback buffer before segment selection, and in hybrid, it uses both RAID-based and buffer-based approach. HTTP Adaptive Streaming was initially implemented over TCP as application-level HTTP standard requires a reliable transport protocol. Despite having reliability and in-order delivery benefits, both HTTP 1.1 and HTTP 2 standard over TCP suffers from head-of-line or hall blocking problem. In hall blocking, a line of packet is held up by the first packet. For HTTP 1.1, the hall blocking problem happened due to limited TCP connections and a delay in a new request queue over existing connections. Although a pipeline feature added later to support multiple requests over a single connection, but it couldn't completely remove hall blocking issue as the response need to arrive in order. In HTTP 2, it supports multiple requests over a single connection and response don't need to arrive in order. But HTTP 2 over TCP have another kind of hall blocking problem. When a packet loss occurs in a TCP stream, it makes all the subsequent TCP stream wait until that packet is retransmitted and recovered. Moreover, for secure connection, TLS over TCP requires an additional handshake. Therefore, in HTTP Adaptive Streaming, such hall blocking and handshake latency may cause unwanted delay while downloading video segments and force ABS algorithm to adopt poor quality segments. In contrast, QUIC, running over UDP, a relatively new protocol with promise of performance improvement over the widely used TCP. It has following benefits, including reduced connection establishment, multiplexing feature without hall blocking problem. Recently, QUIC adopted as transport protocol for HTTP 3 standard. HTTP 3 standard over QUIC uses a single handshake for secure connection and avoids the hall blocking issue from the multiplexing feature. In QUIC multiplexing, each stream is independent of each other and subsequent streams are not affected while a particular stream packet loss occurs. Here an image is presented to visualize what I said for HTTP over both TCP and QUIC related to work. In our work, we divided the related work in the area of adaptive streaming over TCP and QUIC in three categories, where category 1 related work stated that open source implementation for QUIC transport offers poor performance than TCP for adaptive video streaming. On the other hand, category 2 related work stated QUIC offers better performance than TCP for Google provided QUIC server and client. And in category 3 related work, tried to find out and apply new approaches such as MMT, SDN and modification of adaptive bitrate streaming algorithm to get better performance over QUIC. Aim and objective. The aim of our work to evaluate adaptive streaming QoE performance on diverse network conditions over TCP and QUIC transport. We have following specific objective to evaluate HTTP adaptive streaming performance for different state-of-art ABS algorithms, different client streaming reaction and diverse network condition impact. For this reason, we have gone through following two experiments. Experiment 1, QoE performance of ABS algorithm over QUIC and TCP across selected 3G, 4G and 5G network traces for single and parallel dash client. Experiment 2, QoE performance over unstable network with extreme bandwidth fluctuation. Experimental setup. For experiment purpose, we made a testbed containing following components, where Mininet, a network emulation tool used to create streaming network topology containing two OpenBridge switch. To offer HTTP server, we use KD, which support HTTP 3 over experimental QUIC and HTTP 1.1 and HTTP 2 over traditional TCP. QUIC in KD is implemented through QuickCo library, which is based on IETF draft 29 from following reference. Moreover, the server offers a science fiction movie named Tears of Steel. It has 4-second segment duration and 8 resolution across 13 representation rate. To stream video from client-side end, we use Godesh, a headless dash video player. It supports different state-of-art algorithm and to transport to stream video. In addition, Godesh provides potential video streaming logs. Then Linux TC used for emulate different cellular network traces bandwidth parameter between two switch link. And lastly, distributed internet traffic generator used to add cross traffic besides the video streaming traffic. To conduct each experiment, the video content streamed up to 3 minutes and each experiment repeated 3 times. We considered average values of 5 Q metrics such as startup delay, stall ratio, quality switch, average bitrate and mouse values for further evaluation. Let me now turn to discuss about first set of experiment analysis. For this set of experiment, we played video using 3 ABS algorithm, conventional, BBA and arbiter from 3 different categories. We emulated 15 different mobility traces bandwidth from 3G, 4G and 5G network and stream video content over both TCP and QUIC transport. These are the statistics of 15 different traces, where Linux TC applied to change bandwidth parameter after each 4-second interval so that at least 2 segments can download easily under same bandwidth condition. For single client, video played with and without cross traffic, and for 3 concurrent client, video played without any cross traffic. The amount of cross traffic took 20% of average network traces bandwidth between switch 1 switch 2 link. We observed the impact of our video performance using cross traffic for single client was not significant, and due to space limitation in main paper, only single client without cross traffic results were presented. In this result, we observed bitrate and mouse values were higher over TCP transport, and among ABS algorithms, conventional performed the best. For 5G traces bandwidth, we observed over TCP and QUIC transport, the performance was nearly same. For quality switch, there was no actual winner between TCP and QUIC transport, but among ABS algorithms, BVA suffered maximum quality changes and conventional suffered from minimum quality changes. For stall ratio, our quick transport, all the ABS algorithms suffered most stalls. Among ABS algorithms, VBA suffered minimum stalls and conventional suffered maximum stalls. And for 5G traces bandwidth, there was no stalls. The result for all combination startup delay were nearly same. This is due to Godesh uses initial 2 segment for buffer threshold, and ABS algorithms always started streaming with low quality segments. Therefore, at each 4-second interval for all the cases, initial 2 segments download time were nearly equal. From the summary of all the QE metrics, we conclude that for single client, conventional as ABS algorithms and TCP as transport perform better than others. These are the results for 3 concurrent parallel clients. Here we also observe all the QE metrics results were same as single client's results. But due to sharing bandwidth for multiple clients, in this scenario, more stalls occurs and overall performance were less than single clients as natural. Lastly, from summary of all QE metrics, we concluded conventional as ABS algorithms and TCP as transports hold best position. Now moving towards second set of experiment. This experiment conducted on unstable network conditions with extreme bandwidth fluctuations. For this purpose, we selected one driving mobility trace from 5G cellular network. The author of 5G trace source paper stated that 5G traces observed many bandwidth fluctuation due to lack of 5G base station across driving roads, forcing device to use 4G and 3G network. Therefore, for this experiment, one driving mobility trace from 5G network with extreme bandwidth fluctuation was used. This is the state of that trace. Moreover, in this experiment, bandwidth changes after each 1-second interval and single dash client used for streaming the video, and the rest of the combination for ABS algorithms and transport were same as first set of experiments. These are the QE metrics results for single client with cross traffic. For bitrate results, all ABS algorithm received higher values over TCP than QUIC transport, and conventional holds best performance than others. In contrast, most results holds same observation. Similarly, bitrate results. Now for quality switches, ABS algorithms except VBA experience less quality changes over TCP. Among ABS algorithms, conventional was most stable and VBA was less stable in case of quality changes. At below, all the ABS algorithms suffered less stalls over TCP than QUIC, and VBA as ABS algorithm experienced minimum stalls. Lastly, the startup delay results pattern for 3 ABS algorithms and 2 transport is different than previous first set of experiment due to change bandwidth parameters after each 1-second interval causes different delay to startup for playback. This figure we added to interpret why conventional ABS algorithm for both transport remains stable in case of quality changes and holds higher stall than VBA algorithm. We can see in the figure that segment selection for conventional were consistent specifically for TCP, and due to select higher quality, always conventional suffers stall while downloading the segments. On the other hand, VBA always select low quality segments, thus it didn't experience such stall while downloading segments. And throughout the streaming, segment selection were inconsistent. At the end, for this set of experiment, from the summary of all QE metrics, conventional as ABS algorithms and TCP as transport performs better than others. Conclusions and future work. Throughout the investigation for 3 ABS algorithms performance over TCP and QUIC transport, we concluded that TCP outperforms QUIC and RAID-based conventional algorithms performs better than others. Since HTTP adaptive streaming, specifically the ABS algorithms, were designed for TCP in mind, therefore, in spite of having head-of-line blocking problem in TCP, still performs better than QUIC. To deal with the IETF draft mentioned QUIC features, the state-of-art ABS algorithms needs to modification in terms of segment selection. For future work, we plan to extend our experimental study, adding more dashed combination in terms of different segment size duration contents, setting different buffer threshold to playback start over realistic network conditions. Moreover, an alternative implementation of QUIC transport considering the latest effort made by IETF draft. And lastly, it would be interesting to find out a new approach to modify the segment choice decision of ABS algorithms to achieve better performance over quick transport. These references were used throughout the work. Thanks for your attention. I would be happy to answer any questions you may have.